AI or not, our devices are getting increasingly more capable in performing tasks that have traditionally required human intelligence. The proliferation of capable on device hardware has enhanced the capabilities of these devices in areas such as vision, language, and sensor understanding. Convolutional and recurrent architectures have undoubtedly been fueling intelligence over the past decade with significant investment towards their performance execution via hardware, algorithmic, and efficient ML optimizations, along with hardware and software co design. Lately, however, transformers have become the go to architecture for deep learning models with attention mechanism offering unparalleled performance and the ability to model long sequence data with fewer inductive biases. Deployed across all the modalities, including vision, speech, text, these models have demonstrated significant performance benefits across modeling and generation tasks. And the story doesn't end here. One of the key benefit of these models is that not only they can generate the data, but also they can scale to very large sizes, both in terms of data ingestion and parameter size without their performance plateauing. This has given birth to foundation models. Foundation models are large language models that are trained on large corpora of data and act as a universal backbone for a series of downstream tasks. For example, LLMs have been trained on large parts of internet and are able to tackle downstream tasks such as uh, any coding or summarization without explicit training. Despite their accuracy benefits and enabling unprecedented use cases, such models have been pushing the computational boundaries of cloud systems, both in terms of training and deployment. As a result, specialized systems and hardware have been developed for the cloud to accelerate such demanding workload. Typically deployed in large data centers, this poses questions both in terms of sustainability of such deployment as well as the privacy and custody of user data. And that is where this project helps. This project team has created their own infrastructure named as MELT, which is designed to interact, trace, and benchmark LLMs across ML frameworks, devices, and ecosystems. With this tool, they have automated the interaction with instruction fine tuned models and capture events and metrics of interest at a granular level, both in terms of performance as well as energy. Melt is deployed for LLM inference. Their infrastructure is general enough to support the tracing of any workload without user intervention. To the best of their knowledge, this tool is the first to support granular on device energy measurements across device targets such as Android, iOS, Linux with realistic interactions. They have not only produced this, but they have also quantified the impact of quantization on the accuracy of models over different data sets. And this is architecture, which you can clearly see is quite self-explanatory. So this is primarily a device farm, which comprises a combination of hardware and software components working in tandem to automate and measure robustly the on-device behavior of the targeted use case. Their infrastructure adopts the client-server architecture with the coordinating processes running on Raspberry Pi 4, and this is responsible for organizing the execution of the benchmarking suite, scheduling and dispatching jobs to the devices, controlling downstream interactions with the application, monitoring their runtime, temperature, and energy consumption, along with the tracing the events of interest in the downstream tasks. The coordinator communicates with two sets of devices, namely Phone Lab, which consists of mobile devices, and Jetson Lab, which includes NVIDIA Jetson boards, as the name suggests. They also support the monitoring and interaction with graphical user interface and CLI application so that performance can be measured in realistic setting as well as in silos. And you can easily see that the workflow of this melt is quite interesting as it flows very seamlessly from model zoo, which is a collection of the models, to the evaluator, monitoring, and then you can also build them and then run them. They also have done a lot of benchmarking and produced a lot of good results. For example, they have presented the results from running LLMs across devices and platforms with Melt. And they start by describing their experimental setup, and they have also moved on to the on-device evaluation. So they visited the performance and energy consumption characteristic of running LLMs on mobile and edge devices. They measured the throughput and energy efficiency of various models and showed that smaller context models can run sufficiently well on device at the cost of increased power consumption. Also, they studied the device behavior during model loading and sustained inference, along with the power variability during a conversation. They also witnessed high peaks and apparent consequences in user quantization, and they also dove into specific operator runtime and memory bottlenecks. All in all, really good stuff, especially if you look at these benchmarks. They not only show all of these fancy bars and charts, they also prove it with some of the results. For example, while the area of generative AI has seen great acceleration past year, so have the associated workloads. As an area of active research and industrial interest, new algorithmic methods and hardware can provide non-linear scalar and also a new way of scaling the workload. In terms of capabilities, the ability of models to deal with multimodal inputs and outputs become of great value, effectively giving assistance in an extra sense. But overhead of deployment these model is non-negligible, especially on embedded hardware like smart glasses or robotics. That is why on-device deployment of such models emerges as an area of interest, and that is why I'm very interested in this paper, because this looked really groundbreaking to me. So, in my opinion, they have made the first step towards quantifying the performance of deploying LLMs at the consumer edge. They have measured the performance, memory, and energy requirements of such workloads across different model sizes and a heterogeneous ecosystem of devices, pinpointing computational and accuracy bottlenecks. So I think in the future we will be seeing more and more subsequent algorithmic and hardware breakthroughs that will help the realization of new use cases and the democratization of LLM execution in an open but privacy preserving manner. So that's it, guys. Let me know what do you think. I will drop the link to this paper in video's description. If you like the content, please consider subscribing to the channel. Thank you.